Okay, so I'm going to talk about intelligent architectures for intelligent machines, which covers a number of directions in computing, mainly related to data. Because today's computing systems are bottlenecked by data, and data is really key for many, many applications. AI, ML, genomics, data analytics. Important workloads are all data intensive, and they require rapid and efficient processing of large amounts of data. And on top of this, the data they manipulate is increasing. Today, we can generate more data than we can process in many domains. Clearly, the rise of artificial intelligence has been enabled by that, and in part by that, and in part by the advancement of hardware, clearly. And genomics is being much more interesting today with the increasing data. And as you can see, there are a bunch of workloads that are quite data intensive. I'm going to talk about some of these during the course of this talk, and data overwhelms the modern machines when you execute these workloads. And if you look at the mobile end, data is also overwhelming the machines that we design on the mobile systems as well. And this is an area that Jay mentioned that I've been working on for some time now, bioinformatics. And we're specifically looking at genome analysis. And today we're much more capable in generating sequences of genomes of many species, as well as members of different species, because the cost of genome sequencing has reduced dramatically due to the breakthroughs in the devices that we have been able to build in genomics. And if you look at that today, we're not bottlenecked by the devices that sequence genomes. We're really bottlenecked by the computational analysis that we can do on them. So the scientific discoveries, as well as medical advancements, are very much dependent on the speed and the energy of the computational analyses that we can do with the output of these devices. And this is one example device that we've been examining for some time now. This is the Oxford Nanopore device. It's not the smallest version of their devices. The smallest version you can plug into your cell phone, actually. But you can sequence genomes, and there are a lot of bottlenecks in terms of data analysis that I'm not going to go into. If you're interested, we have recently written this survey article that covers a bunch of the work on genome analysis, and it looks forward in terms of how to accelerate these systems. And I believe specialization of algorithms and hardware and algorithm architecture co-designed together can enable much better and faster, as well as much more efficient analysis of genomes that we would like to make real time. And this is one of the recent works that we have published in the area. There's more ongoing, and I'd be happy to talk about it. But this is just one example of applications where data overwhelms modern machines. And I believe this is a very interesting example because there could be much more that can be enabled, new computing platforms that could be enabled for genome analysis, for example, if you design architectures very well. But today, this talk is about the fact that we're not designing architectures very well to handle data, because data today is overwhelming our storage and memory capability, communication capability, as well as computation capability in the end. And it greatly impacts robustness, energy, performance, and cost. And if you go to the fundamentals, a computing system consists of three key components: computation, communication, storage, and memory. And over the course of 7 decades or more, we've heavily optimized the computing units. We actually do a lot of very interesting and very sophisticated things in the computing unit to maximize performance, maximize energy efficiency. But this came at the expense of mostly ignoring what remains off the computing unit, which is the communication and memory and storage units, to a first order, of course. And as a result, we have systems that look like this, more or less. This is a cartoonish picture that I drew more than 12 years ago, actually, for an NSF proposal that I was writing at the time. But this basically shows that you have a multi-core system. You can imagine these cores as agents and accelerators also today. And these cores are a very small component of the system that we design today. Most of the system is really dedicated to storing data, moving data, storing data, moving data, controlling the storage and movement of data, storing more data, moving more data, and storing even more data. So more than 95% of a single node today is really dedicated to data storage and movement. So we're calling these systems computing systems, but maybe we should really be calling them storage and data movement systems. And this comes because we made some choices in terms of processor centricity in these designs. And this talk is about how to maybe fix those choices going into the future. So as a result of this processor-centric design paradigm, data is overwhelming our machines. I'm going to talk about this paper in a little bit later on. But we've shown that on these workloads that I showed you in this picture, more than 60% of the entire system energy on a mobile system is spent on data movement today. So my axiom going forward will be that if we want to design intelligent architectures that behave intelligently, we should really start from handling data well, because data is going to be at the core of the intelligent functions that we put into the devices going into the future. So this, of course, begs the question, how do we handle data well? I believe there are three components over here, which I don't think we will have time to focus on all, but I will focus on the first one especially. And if you have time, or if you think it's beneficial, I am happy to talk about the other two as well. First of all, we need to ensure that data doesn't overwhelm the components. We need to design intelligent algorithms to minimize data movements and data. And we need to design intelligent architectures to do the same. But more importantly, I believe we need to focus on whole system designs, cutting across from algorithms to architectures to devices to minimize the data. Second, I believe we need to take advantage of vast amounts of data and metadata that we see in our systems to make our decisions better. There are a lot of components in our system, controllers, schedulers, etc. They make architectural and system level decisions, and they don't learn from their actions that they've done in the past. But they could easily learn if they actually take advantage of the data and metadata, and they actually have a learning algorithm built into them. So I'm going to hopefully talk about this briefly. And third, I believe we are not doing well in terms of understanding and exploiting properties of different data, and we need to do that more and more going into the future, because if we can distinguish the properties of different data and different usage of data, then we can perhaps improve the algorithms and architectures in different metrics. We can use only the minimal amount of data that we need to actually get a task done, for example. And I will talk about this also briefly. So given that these are three components on how to handle data well, how are architectures today doing? I believe they're not doing well, basically. They're today designed to mainly store and move data versus to compute on data, because they're processor-centric as opposed to data-centric. As a result, they're overwhelmed. So we're going to talk a lot about this data-centric architectures. Second, architectures are not taking advantage of vast amounts of data and metadata that's available through them. For example, I have the cell phone for some number of years now. Actually, this is a new one, but I had an old one that I used for 6 years. And for 6 years, the cell phone had a memory controller in it. I'm going to pick on the memory controller, but all of the controllers, you can generalize what I said to all of the controllers. This memory controller saw a lot of requests that are coming from different applications, but it didn't learn anything. Basically, it was designed to take some action in a given state, and it always kept taking the exact same action in the same state. So it never generalized. It never tried to figure out whether that action was good or bad for some performance metric or some energy metric. So basically, it was designed to make simple decisions, ignoring lots of data by design, because it was designed to make human-driven decisions as opposed to data-driven decisions. As a result, it lost a lot of opportunity to adapt to the system, workload, operating conditions, etc., at both the fine grain as well as the coarse grain. Even though it could have learned a lot within a course of a millisecond, it didn't learn anything over the course of 6 years. So I believe we need to change this, because as humans, we claim to be more intelligent than a lot of species in the world and in the universe also. Maybe that's a bit too much, but I think we are a little bit intelligent in the sense that we can learn from our past actions. Whether or not we employ the learning is a different question, of course, but our machines are not able to learn from their past actions currently, and I think we need to change that. So on the third aspect, architectures today are not good at knowing and exploiting different properties of application data. They're designed to treat all data as the same. So if you look at a piece of data, it doesn't get communicated, its properties doesn't get communicated to the architecture well. So I don't know at the architectural as well as the system level whether this piece of integer, let's say, I don't even know whether it's an integer sometimes, right? I don't even know whether something's a pointer. But I don't even know how can I approximate it. What are the safety and security properties? What are the compressibility properties? What are the privacy properties? And you can actually list a lot of other properties. And because this information about data is not communicated to the architecture cannot make data-aware decisions that can adapt to the characteristics of data. As a result, architectures today make component-aware decisions, and they're inefficient because of that. So all of these three properties, I believe, are important to satisfy for future architectures: data centricity, data-driven decision-making, and data-aware algorithms and systems. And as I said, I don't have time to talk about all of them, I believe, but I'm going to focus more on the data-centric architectures today. But I'm happy to talk about it if you think we have time. So what is a data-centric architecture? I believe when I first started thinking about this, I listed 4 properties. I'm open to learning more properties, but these are the 4 properties that cover a wide range of properties overall, I think, or sub-properties. I believe if you want to be data-centric, you need to process data where it resides. You don't want to move data much. So this is processing data where it makes sense, in and near memory structures. Minimize data movement as much as possible. Second, I think we need to respect the data. Sorry about this. Somehow my computer has its own mind. Meaning we need to enable low latency and low energy data access, because data is the most important thing that we're dealing with in the system. And I think this is very important going into the future. For example, main memory systems that have low latency and low energy. I know there's work going on at SNU related to this. So I'm not going to talk about this aspect, but I think it's going to be a lot more important going into the future. Okay. Third, low-cost data storage and processing. I think this is very important. I'm not going to talk a lot about it, but this will cause a lot of problems going into the future as well because of the technology scaling issues. By the way, I'm hearing some noise. Is there some question or? Okay. Okay. Third, I think we need to manage data intelligently. We need to design intelligent controllers handling robustness, security, and cost. And this is going to be one of the motivations that I'm going to provide for processing data where it resides. Okay, so let's jump in and talk about processing data where it makes sense. And I think this is a very broad concept. Today we're processing data only in the processor and the accelerators, and really nowhere else in the system. We should probably have a distributed processing engine where we can process data where in the disk, in the SSD, in the memory, in the caches, while it's moving, etc. So we should have the capability to be able to do that. And this is not a new idea. This is an old idea, especially the processing in memory part is an old idea. And this is the first general purpose paper that I've encountered on the topic. If you find an older paper, please let me know. This is by Harold Stone, who has written a nice computer architecture book in the 1990s also, if you may have studied that perhaps. And basically here he argues that we should be processing data near where data resides inside memory essentially. And it's a beautiful paper. I recommend doing that. And clearly this is an idea, I recommend reading it. Clearly this idea has been examined for decades, for 5 decades clearly at least. And it has not panned out. But I believe we're in a special position in the last 5+ years that we need to re-examine this idea in a different way. And let me actually motivate that special position, in my opinion. Today, basically, we're kind of squeezed between technology and applications and systems. We're having a huge push from technology telling us to have intelligence in our memory controllers and computation capability. And we also have a huge pull from applications and systems that are also telling us the same thing or a similar thing. And we're kind of squeezed in the middle. So we should really do something about how we deal with data inside our memory controllers. So I'm going to motivate these 2 aspects, hopefully relatively quickly, but hopefully it'll be interesting also. Basically, the push from technology is that today our main memory technologies are not scaling well. As a result, industry is open to new architectures and new functions inside or near memory. We're already putting controllers close to DRAM with hybrid memory cube or high bandwidth memory type of 3D stack or 2.5D stack architectures that enable low latency, high bandwidth, low energy access to a logic layer from memory layers. And people are experimenting with different architectures, and there are even more experimental devices like monolithic 3D architectures. And this is happening because memory scaling has been an issue for a while. This is an older paper that we wrote on the topic in 2013 when we did not have a lot of evidence in terms of memory scaling. We were working on gathering it. But this is one of the example evidences of memory scaling issues. Basically, we did this study with Facebook about 6 years ago, where we showed that the server failure rate that is observed in production data center servers across all of the servers that Facebook has is heavily correlated with the DRAM chip capacity that's employed in the server itself. So there's a very positive correlation, and this is because chips that are denser are more vulnerable to errors. If you're interested, I'd be happy to talk about that more. We also built a lot of low-level infrastructure, FPGA-based infrastructure, to understand these scaling issues, retention issues, read disturb issues, latency issues, etc. And this is our older infrastructure on the bottom over here. And this is our scaled infrastructure. And we actually released this infrastructure. People are using it. I'm going to mention that in a little bit. You can actually do relatively easy studies with C++ API, test memory chips, essentially. While we were doing that, we basically stumbled upon, together with Intel, the Rowhammer issue. Essentially, one can predictably induce errors in most DRAM memory chips that you buy in the field today. And I'm going to very briefly talk about this because I think this is one of the big motivators for putting intelligence inside the memory controllers. And I know that Jay has been doing work on this also. Basically, one can predictably induce bit flips and also Sungju, by the way. There's a lot of work, good work coming out of SNU on this topic too. But basically, one can predictably induce bit flips in commodity DRAM chips today. And this is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And clearly, people are writing interesting articles that say, forget software, now hackers are exploiting physics. And there's clearly a big push in the hardware security community into figuring out this sort of vulnerabilities and ensuring that we don't have them going into the future. But I believe that it's going to be not so easy not to have them into the future without having intelligence in our memory controllers. So what is the Rove hammer issue? Most of you probably know this, but I'm going to quickly explain for those people who may not know. Essentially, in today's DRAM chips, you can activate a row to be able to read it, which applies high voltage to the word line. And then you close the row so that you can activate some other row, which applies low voltage to this particular word line. So this is called an activate precharge pair. Now, if you keep doing this, activate precharge, activate precharge, activate precharge, activate precharge repeatedly on a single row, it turns out physically adjacent rows, if they're vulnerable, and the vulnerable bits in those adjacent rows gets bit flips. They can flip from 1 to 0, 0 to 1. Clearly, this should not happen because you're not even writing anything to the row, but you're not even touching these adjacent rows. So that's a read disturb phenomenon. It's a very fundamental phenomenon in many memory systems. And DRAM is interesting because if this gets exposed into the field, it directly impacts your data structures that are stored in memory, and it could be a security vulnerability. And when we did our testing with the infrastructure that I showed you earlier, we found out that more than 80% of the chips that were manufactured by 3 major manufacturers were actually vulnerable to the Rove hammer bit flips. And this is a scaling problem because older chips do not have this problem. It happens only in younger chips. And it depends on how you actually hammer. I'm not going to go through the details of it, but it's a fascinating phenomenon. It's not going to go away because fundamentally it's getting worse. The number of hammers, the number of activates you need to do to induce bit flips is reducing. Okay, so the big problem with this sort of bit flips, whether they're induced by Rove hammer or retention or some other phenomenon, is if you can actually control them somehow, you can threaten the security of a system. Basically, one can take over an otherwise secure system, and we discussed this issue in our earlier paper. And Google folks built attacks, beautiful attacks actually, beautiful security engineering attacks that exploit this Rove hammer problem to gain kernel privileges. And later, a lot of other folks built a lot of attacks that I'm not going to talk about. But I will quickly mention that to be able to solve this problem, you need some intelligence inside the memory. I believe memory controller is a good place to put that intelligence, so that the memory controller understands what's going on. And there are multiple approaches to this problem, clearly. You could potentially figure out whether an attack is going on, or you could try to intelligently refresh different parts of memory to ensure that an attack doesn't happen. But these are both different types of intelligence that you add to the memory controller to fix the issue. And if you're more interested in there are a bunch of articles that are related to this that we have written. This is an older survey that was invited to TCAT, which I'd recommend you to read. What this doesn't cover is some new analyses as well as solutions, potential solutions in 2020. I'll very quickly talk about it. Basically, in this work, we've tested more than 1,500 DRAM chips, and we basically showed that the scaling is getting worse. You can actually induce bit flips with only 4,800 double-sided hammers in the worst DRAM chips of today. And chips of newer DRAM technology nodes exhibit much worse characteristics, essentially. You can read the paper for more detail. And the existing mitigation mechanisms are not very effective, especially if you scale to very, very low hammer counts like hundreds. And we actually also showed that the security solutions that are incorporated into the DRAM chips by the manufacturers are not working well, because these manufacturers claim that they have Rove hammer free chips after they manufacture DDR4. Unfortunately, they never disclosed what they exactly did to make the Rove hammer chips Rove hammer free. And and we were able to actually reverse engineer some of that and show that you could actually do hammering such that you could bypass those presumably secure solutions. So I believe going forward, we need to have more security-oriented and more open solutions to solve this problem. And if you're interested, I think the solution is going to be intelligence in the memory controllers. And okay, I talked a lot about Rowhammer probably since it's fascinating clearly, and I'm happy to talk about it more if there's another discussion related to it. But it's not just about Rowhammer. I should also say that. Scaling is a bigger problem. Rowhammer is a very interesting example of it, and perhaps very ominous example of it clearly. But retention is also a scaling problem, and we've been looking at reducing refresh in DRAM for a long time now, because as you scale the size of a DRAM cell, it becomes much more difficult to determine the retention time of every single DRAM cell, and profiling times increase. And as a result, manufacturers are now putting in error correcting codes, for example, to ensure that you don't get random bit flips due to retention time problems like variable retention time. I'm not going to go through this in detail. You can actually take a look at a bunch of the papers that we've written. I'm happy to talk about them if there's interest. But these papers actually all point to the fact that you need to have intelligent controllers if you want to get rid of refresh as much as possible, and if you want to minimize the retention-related issues in your system. So this is another example of why we need, in my opinion, intelligent memory controllers. And industry is also writing papers about it too. This is a relatively old paper by Samsung and Intel, two companies that don't normally talk to each other, in my opinion. But they were able to write this nice paper, 4-page paper, in the Memory Forum in 2014, where they basically said DRAM process scaling is becoming harder, and by having intelligent memory controllers and co-architecting controllers and DRAM together, we can actually do much better. There's another reason why I believe we should have intelligent memory controllers. Again, this is a scaling problem, because there's no single technology that's scaling very well. Today, it makes sense to actually, or that is good at all metrics, let me put it that way. Today, it makes sense to put multiple different memory technologies, for example, DRAM and phase change memory, or DRAM and multiple different other types of DRAM, such that you get the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. Of course, to be able to do that, you need to have an intelligent controller that understands what data you put to different technologies and how you would maximize the greens of each technology while minimizing the reds of each technology. So this is another reason why we should have intelligence in the memory controller going forward. And I can keep going on and on, I believe, related to this, but my computer doesn't want to continue. No, okay. I guess skipping that helped. Okay, I can keep going on and giving more examples of intelligent memory controllers, the need for intelligent memory controllers, but I'm going to stop here. But at to roll back, essentially, all of these scaling related issues are pushing us to do something else with the technology. And we have never had these scaling issues in the past before. So DRAM has a long history, almost 60 years of history today. And DRAM has been scaling extremely well in main memory. The scaling issues started appearing, especially in the last 5 to 10 years. Okay, so let me give you the higher level perspective. We have a huge pull from systems and applications today that are pushing essentially or pulling us to do something else, do computation near memory. Why? Today, data access is a major bottleneck. Energy consumption is a key limiter, and data movement energy dominates compute energy. So I'm going to look at these very quickly in different perspectives. But basically, I think we actually have a bigger responsibility going into the future. And I think that responsibility is, do we want a future that looks like this, a beautiful world where we can breathe in and live nicely in, or do we want a future that looks like this? And I would argue that we want the best of both worlds. We want the high performance and productivity of a world that may look like this, while having the energy efficiency and sustainability of a world that may look like this. So how do we get there? Before we think about how do we get there, I think we should also identify the problem that is limiting us from getting there. Today, data access is the major performance energy bottleneck, and our current design principles in all computing systems that we design cause great energy waste. And they also cause great performance loss. And this is because data is stored far away from memory, and essentially we need to move the data a lot in the system. So this causes great performance loss, but I put this in parentheses because we try extremely hard at all levels of the stack to avoid that performance loss as much as possible at the expense of higher complexity in our systems. Basically, we add a lot of mechanisms to our software and hardware, for example, massive amounts of multi-threading to overcome the latency, hide the latency, many levels of caching, heavy levels of out-of-order execution, and also many levels of prefetching as well. So all of these add complexity to the system to overcome the performance loss, and they don't always overcome the performance loss. Sometimes actually they're very ineffective because applications are just too data intensive and they have dependencies or random access patterns that none of these do well at. As a result, they cause even more energy waste. So today we're in a vicious cycle where we have a data access problem, and instead of really solving it, we're trying to tolerate it with different mechanisms that causes even more energy waste. And we keep increasing the energy waste, in my opinion. And as a result, the amount of energy spent on compute is increasing significantly as a fraction of the energy spent in the world. So I believe we need to identify the problem. And the problem is really, as I said, processing of data is performed far away from the data. And this is because we're very processor-centric today. All data is processed in the processor, and everything else is essentially dumb. They cannot do actions on the data. Yet we very well know that memory is a big bottleneck. So clearly, people have written a lot of papers related to this. This is something that I would recommend. This is Dick Seitz, who designed the alpha processors in the 1990s, the cutting-edge processors. And later, he wrote this one-page article in Microprocessor Report, where basically he said that the memory stupid. That's the title of the article. That says, we designed this processor to finish 4 instructions per cycle, but it's finishing one instruction every 4 to 5 cycles. So it's operating at 1/16th to 1/20th of its peak bandwidth on this important data-intensive workload. Why? It's waiting for memory. So he finishes this article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. So fast forward about 10 years, this is data from my own PhD thesis, run at execution. We essentially showed a very similar thing together with Intel. We basically showed that more than 55% of the time in a cutting-edge Intel processor is spent waiting for data. And if you don't believe me or Dick Seitz, today a lot of people believe Google, I believe. I think, and Google has shown in this beautiful paper that they've written in ISCA 2015, essentially the same thing. Sorry, somehow this computer is moving by itself. I had to solve that problem. But basically in this nice paper, Google showed that a cutting-edge processor in 2015 is waiting for data most of the time. It's really processing, finishing instructions only 10 to 20% of the time. And this is because it's very processor-centric. So basically, processor-centric design leads to a grossly imbalanced system. And this is energy inefficient, low performance, and complex. And as a result, data moves a lot because of this design choice. And to tolerate this, we make our systems even more complex and bloated. This is true for accelerators as well, not just the processors. If you look at a machine learning accelerator today, for example, most of the resources are actually dedicated to data movement and data orchestration, and to ensure that the data is there so that you can actually do the multiply and accumulate operations that you need over there. So we basically design these complex hierarchies and mechanisms. As a result, it's energy inefficient, low performance, and complex. Okay, so we're back to the picture that I showed you earlier. Most of the system is dedicated to storing and moving data as opposed to computing on the data. So very quickly, the energy perspective, this is a slide that I borrow from Bill Daly. This is a relatively old slide. The numbers have changed, but the takeaway hasn't changed over the course of 6 years. Basically, this slide shows that a 64-bit double precision floating point operation is very cheap in terms of energy today. It's about 20 picojoules, and a DRAM read or write is about 16 nanojoules. So that's about 800x difference. So this, of course, begs the question, if you don't have good locality to compensate for this difference, does it really make sense to bring two operands of a floating point operation all the way from memory, do the operation inside the chip, and write back the data once more, consuming 800x energy to the memory? Essentially, if you do that, you haven't, and if you cannot amortize the cost of all that energy, you will be wasting a lot of energy just to do a simple floating point operation that's really cheap today. So just to give you a historical perspective, the numbers were not like this 70 years ago. So if you go back 70 years and to do the scaling studies, it's not an easy study to do easily, of course, because the numbers are not as easy to get from the 70 years ago. But an add operation, let's say, was much more expensive than a memory read or write at that time, about 1 to 2 orders of magnitude. So what happened over the course of 70 years is logic scaling worked really well. We were able to technology scale our logic, and as a result, its energy, performance, etc. improved. But the interconnects and memory did not scale very well. As a result, we're spending a lot of power and energy on the interconnect as well as latency. Okay, so there are other studies that show that a simple add operation or a complex add operation actually is much less costly in terms of energy than a memory access. I'm not going to talk about those in detail, but this is also reflected in the data movement results that I have mentioned earlier. More than 60% of the total system energy as a result goes to data movement in important applications. So I would argue that we do not want to move data especially when we're dealing with a lot of data. So we need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, and I believe wherever data resides, and wherever we move the data. So we don't want to limit ourselves to memory, cache, storage. We want to do it everywhere, including the network. And we would like to make computing architectures more data-centric as opposed to processor-centric. So I think in the rest of the talk, I'm going to single out memory and talk about memory, even though I said this should be done everywhere. But I think memory is really interesting and special because today we actually, because it's big, clearly we can design very large memory systems today, and we can store a good chunk of our applications inside our main memory systems today. There are in-memory databases, in-memory graph processing engines, in-memory media processing engines because of that reason. It's hard to do that with the caches because they're much smaller. And if you want to make them bigger, they become much more expensive, clearly. SSDs are very, very interesting also, but they are not as low latency as memory. So ideally, memory is still very special in this case. So of course, there are many, many questions to enable processing inside the memory. We have these applications. We would like to be able to query the memory using a processor or an accelerator. Ask the memory, can you execute this function for me? And the memory says yes or no. And if it says yes, it gives the results back. And there are many questions. I'm not going to cover everything, but I think we need to solve. Sorry, if is there a question? Okay, maybe not for me. Sure. Okay. Okay, sure. Yeah, I don't understand Korean much. Okay. So basically, how do we design the memory and the controllers? How to design the processor chip and in-memory units and the accelerators that go along with it? How to design the software and hardware interfaces to enable this? How to design the system software, compilers, and languages? And algorithms and theoretical foundations. So this is really an exciting across-the-stack problem, and there are a lot of opportunities all across the stack. Algorithms to devices, and also the interactions in between. In the end, I believe we need to look at all of the questions. And I also would like to mention that theoretical foundations is very interesting also, if some of you are interested and inclined towards theory. If you look at the way we do computing theory today, we count operations, right? We count computations, the big O notation, big theta notation, all of those. Computational complexity theory is based on how many operations we do. It does not take into account data movements or the memory size or etc. As a result, fundamentally, it's processor-centric. So there's this unspoken assumption about computational theory today, which is really processor-centric. And I believe if we really want to build a data-centric system, we need to revisit the computing theory as well going into the future. So it will be disruptive, but I believe we need to start simple as well. So I'm going to talk about how to start, in my opinion, going into the future. I think there are at least two new approaches compared to past processing in memory systems. In the past, people have designed very interesting systems, but some of them were not as cost-effective, in my opinion, because people wanted to put huge computing units inside the memory chip. I believe maybe medium computing units may work, but huge computing units are not going to work really well because fundamentally the DRAM process and the logic process are not very compatible. But going forward, of course, if there's a technology that can combine these better, then that should also be examined. And I think monolithic 3D technologies are the technology that gets closest to that combination, but there are also challenges in monolithic 3D today. So I'm not going to talk about monolithic 3D, even though I believe it's a special case of number 2 over here. I'm going to talk about how do we minimally change memory chips to essentially get a lot of the functions that we may actually benefit from without a lot of cost. And the second is how do we exploit advanced and 3D stacked memory to actually get even more benefit out of processing in memory. Of course, these approaches can be combined together as well. So let's start with the first one. So first one I call minimally changing memory. It's also called processing using memory. Essentially, any type of memory, it has a great capability to perform bulk data movement and computation internally with small changes. You can exploit internal connectivity inside the memory to move, copy data, or you can exploit analog computation capability. And you could do even more. For example, add more internal connectivity, add more computation capability. And I'll give you some examples from our own research, and I'm also going to mention some other research that are relevant. Clearly, there's a lot more research going on, especially in the non-volatile memory systems. And even though I'm going to give you examples from DRAM, all of the ideas are actually applicable to non-volatile memory, and non-volatile memory can do even more going into the future. So I'm going to start simple, not even talk about computation, but we're going to look at data copy and initialization really quickly. This is a very important primitive. Copying and initializing data is very necessary in many, many applications. And Google recently showed in the paper that I mentioned that more than 5%, or approximately 5% of the entire data center execution cycles is spent on just these two function calls, memmove and memcopy. So this looks not so great for the overall execution time. Clearly, there's a lot of data movement that's going on in the system beyond these function calls, but these two function calls are responsible for 5%. That's a lot. So how are we doing the data movement today in a system today? Basically, we go through the processor, because we're processor-centric, right? Memory cannot do any action on the data, so we have to go through the processor to copy this white page to this gray page. So to be able to do that, we need to copy the or bring the white page byte by byte on the all the way into the L1 cache. We need to copy, do the copy in the L1 and do the write back. This is high latency clearly because you need to actually do 3 times 4 kilobytes, assuming this is 4 kilobytes. This high bandwidth utilization, you move a lot of data. You could cause cache pollution, but you could actually eliminate that by doing this through the direct memory access engine today in the memory controller. And this causes a lot of unwanted data movement, especially if you're not going to use the data that you copied. It's a lot of data movement for no reason, essentially. Initialization is also a special case of copy. So if you're initializing a 1 terabyte database, for example, you're actually doing a lot of data movement just to initialize the data. So for a 4 kilobyte page copy via the direct memory access engine, not even going through the cache hierarchy with DDR3 technology, but DDR4 doesn't make it much better actually. But with DDR3 technology, in the paper we show that you can actually, you need to actually spend more than 1,000 nanoseconds and 3.6 microjoules. So if you show this picture to a 10-year-old child and ask them, is this a good way of doing things? Maybe they will tell you, okay, why do you involve the CPU in this? Just do it inside the memory. All right. So if you do it inside the memory, you could take advantage of the internal connectivity, which makes it low latency, and also you don't go through the high latency interconnects over here clearly. You basically reduce the bandwidth utilization on most important bandwidth constrained resource in the system, no cache pollution, and no unwanted data movement. So I'm going to show you a mechanism that basically takes us 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules in an unoptimized manner. If you optimize it, you can do even better, I think. And the idea is very simple. Once you recognize what's going on, and I think once you know the internal VM microarchitecture, we call this idea row clone. It's relatively old right now. But the basic idea is if the two pages or rows are in the same subarray, which means that they share the sense amplifiers, row buffer, you can do this copy by doing 2 consecutive activates. Essentially, you first activate row A, which brings the data into the sense amplifiers in the row buffer, and then you activate row B, which implicitly disconnects row A from the sense amplifiers, but the data stays in the sense amplifiers, and it connects row B to the sense amplifiers, which means that the row buffer drives the data that it stores into the destination row because it's much stronger than the cells. Essentially, with 2 consecutive activates and negligible hardware cost, you can get more than 10x latency reduction and more than 74x memory energy reduction. Clearly, we would like to generalize it to the DRAM chip. So you want to be able to do inter-bank copies and inter-subarray copies. These results are from 2013. We have improved those results with some more recent work that I'm not going to talk about. So for example, you can do faster inter-subarray copy. You can enable data movement at smaller granularities within a bank. You can do faster inter-bank copy if you actually add a little bit more interconnect into the system. And I'm going to talk about the computation idea. So I'm just going to go through these. But basically, these show that you can do much better copies inside memory, not just in a subarray, but across the subarrays, as well as across banks, if you add some more support and essentially some more connectivity to be able to do those copies. Okay, so basically, I'd like to mention the thinking here. Essentially, we're thinking of memory as an accelerator. Memory is very good at doing this copying internally or initialization internally. So we would like to add the support to memory, just like we would add support for any other accelerator in the system. So we're treating memory similar to a conventional accelerator, so it's going to have similar programming issues like those accelerators, I believe. But it has one big advantage compared to other accelerators. It's sitting on the other side of the memory bus, whereas all of these accelerators that we're building in our system are actually limited by main memory. But main memory is not limited by main memory because it's on the main memory side, as you can see. But of course, this is going to come at a downside as well. This is going to exacerbate the programming issues a little bit more because it's not going to be processor-centric anymore. You need to think about it a little bit differently in terms of programming. Although row clone is a special example where you don't need to change things a lot. Okay, so let me talk about in-memory operations as well. Similarly to row clone, copying and zeroing or initialization, we can support and or not and majority function at low cost by using the analog computation capability of DRAM. And the idea is very simple. We activate multiple rows, and if you do that, you can perform analog computation through charge sharing. And this leads to significant performance and energy improvements. Now, before I give you the mechanism a little bit more, I will mention that new memory technologies enable even more opportunities into the system. Basically, there are a bunch of memory technologies that are really interesting that are non-volatile. They can operate on data with minimal movement because DRAM fundamentally is destructive whenever you do a read or activate, whereas these memory technologies are not destructive, so you can actually minimize the data movements. In DRAM, you need to move the data a little bit somewhere. And these memory technologies are also able to do analog matrix vector multiplications because of the way the crossbar memories are designed. So they're actually even more how should I say, even more capable than DRAM for doing computation. Okay, so let me go over this triple row activation. I see some things on the screen. I hope I didn't do those. But anyway, I don't know how to remove those. Let's see. Subtitles. I don't want to do that. Don't allow. Okay. Subtitles are not available. Sorry. Okay, so let me talk about how we do this in DRAM. Essentially, if you activate concurrently 3 rows, A, B, C, you connect these bits that are on the rows concurrently to the same bit line. And essentially, this performs a bitwise majority function. If at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So in this case, you get a VDD, meaning that because at least 2 of these cells were charged, you get the charge state. So this is a bitwise majority function. So this is very powerful because now you're doing bitwise majority on the entire row. Imagine this row being 8 kilobytes. And imagine that you have the capability of doing this across 1,000 subarrays in a DRAM chip. So you can operate on 8 million bits concurrently at the same time to do a bitwise majority. So clearly bitwise majority is interesting. In fact, you can actually transform your algorithms to bitwise majority functions. And we have a paper coming up in ASPLOS in 2021 talking about how to do this transformation in general purpose programs. But I'm not going to talk about that. But if you actually take C out, if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So now you can do a bitwise AND and bitwise OR depending on the value you create into C. And you can expose to the ISA. I'm not going to talk about this. To be able to make this low cost, you need to actually combine it with row clone, and you need to actually designate a small area in the DRAM chip to be able to do this effectively and at low cost. So now we can do AND and OR. What is missing is NOT. And to be able to do NOT, you need to actually add a little bit more overhead into the DRAM chip. Essentially, the complement of a bit actually exists on the other end of the bit line after you activate that row. We just store that bit through another interconnection to a special row inside the same subarray by feeding the negated value in the sense amplifier into a special row. So this adds a little bit more overhead. I don't think it's a lot of overhead, but once you actually do this, you get significant performance and energy improvements in terms of knots, as you can see. And you're functionally complete. You could potentially transform any algorithm if you actually lay out your data nicely, and if you actually think about your algorithm differently, you could potentially transform any algorithm to the bulk bitwise combination of NOT and ORs. And clearly you can build other primitives on top of that. Okay, so you can do that, but there are some algorithms that are naturally very much fit for these bulk bitwise operations. And examples include bitmap indices in databases, which operate on many, many large bitmaps, and they lead to a lot of bitwise operations. People actually design these databases especially to maximize those bitwise operations so that they can map better on GPUs. The Bitweaving database is an example. Microsoft has a web search engine, Bitfunnel engine, that is has a very similar concept. And we have other examples, encryption, set operations, and DNA sequence mapping I'm not going to talk about. But if you actually map those algorithms to what I just described, bulk bitwise majority, bulk bitwise AND, NOT, and row clone operations, you get significant end-to-end performance improvements in simulation. You can see that it's about 6.6x in the best case for one query using Ambit. And if you actually take a database that's specifically designed for maximizing these bitwise operations, you get even more performance improvement. And performance improvements actually increase with the size of the data. Of course, at some point you hit a limitation in terms of the size of your memory module. You have to partition the data across memory modules and minimize the communication across memory modules whenever you want to do merging of data, for example. Okay, so I'm not going to talk about this more, but I believe this is really promising. And if you can read the papers that we've written on the topic, this is a book chapter that we've written that talks about some future directions as well. And this is a coming up work that I mentioned earlier. This proposes a programming and system framework for bit serial SIMD processing based on Ambit. So let me quickly talk about some work that actually shows that this row clone and bitwise operations, like I discussed, is actually very much possible in a limited set of DRAM chips today. These folks from Princeton took our soft-MC infrastructure that I mentioned earlier, and they basically showed that by reducing the latency parameters, by violating the latency parameters of DRAM chips, you can essentially do row clone operations in off-the-shelf DRAM chips without changing the DRAM chips at all. By just changing the memory controller in the soft MC. And you could actually, with a limited set of DRAM chips, you can actually do AND and NOT as well. So even though the DRAM chips are not designed to do these operations, this is a proof of concept that shows that DRAM chips are able to do these operations in a limited manner, of course, because they're not designed to do that. So imagine what could happen if you actually design the DRAM chip to do these operations reliably. And I believe that's the right way to do, but this proof of concept is very important, I believe. And also you can do these operations in other emerging memory technologies, which I'm not going to talk about. This is one paper that talks about bulk bitwise operations in phase change memory and other resistive memory technologies. And clearly these non-volatile memory technologies can do even more that I'm not going to talk about since we don't have time. But I have longer, I'm happy to talk about it if you're interested. Okay, so I'm going to talk about the second direction now. If there are any questions I can take either now or later or at the end, I'm happy to take any time. So I see something on chat. Let's see. Okay, let me read it actually. You keep mentioning how we should compute even in non-DRAM memory. Personally, I don't think the PIM or NMP ideas in main memory like bitwise operations or vector reduction operations will be as effective when it comes to cache or interconnection scenarios. Is there a certain application or operation you had in mind when you mentioned computing cache interconnection networks? So I think this is a longer discussion, frankly. I think it's possible. I think there's work, for example, that was done by Michigan that shows in-cache computation that showed some benefit on neural network applications. Of course, I think what you're getting at is perhaps the size of the data. If you can fit the size of your data inside your caches, I believe caches could be very effective in terms of doing these operations. Clearly, if your caches cannot host a large chunk of the data that you're dealing with, that you're computing on, then they will not be very effective. Then you will need to get as much locality as possible from your caches and do these operations in your caches. So certainly you will, in caches, potentially it's a bit harder if your data doesn't fit into your caches to begin with. Interconnects, I'm going to leave that for discussion potentially, because I think interconnects are certainly interesting. Like, where do you do the computation becomes an issue over there. Do you do it in the router, for example? Do you do it, what kind of operations do you support? I believe, for example, the NYU Ultra computer supported fetch and add operations. I believe that's very interesting. That's usually good for synchronization, for example. But how do you do it general purpose becomes more difficult, clearly, in the interconnect, in my opinion. I think caches can be more general purpose, but again, their capacity is limited. Okay, I guess feel free to keep posting, as Jay mentioned. I'm going to continue since I don't see any other questions. So let me talk about this other opportunistic direction. Today, 3D stacked memories exist. How do we take advantage of them to do processing near memory? So this is processing near memory, whereas the previous one that I mentioned was processing using memory. So we're not going to do things inside the DRAM layers here. We're going to do things inside the compute layers. And we have today technologies that can put DRAM layers and compute layers together with high bandwidth, low latency connections, such that, and then we can put any kind of logic inside the logic layer, as long as we don't overcome the power restrictions as well as the thermal restrictions of the device. And I believe true three-dimensional technologies like the monolithic three-dimensional technologies or the next work at Stanford and other places actually very interesting as well going into the future. But I'm not going to talk about those emerging technologies. I'm going to talk about more 3D stacked traditional technologies, and these clearly exist as early as 2010s or so, and they're improving going into the future. So I think there are many questions here. How do we use this 3D stack processing in memory? I like thinking about this. What are the maximum things we can do in this device, and what are the minimum things we can do? And the maximum thing is usually application specific. if we had the entire freedom in the world to change the entire system, including the programming model, virtual memory, coherence, etc., what can we do? What kind of benefits can we get? Or if we had a little bit less freedom, can we do something simple function offloading to get some benefit? And then what is the minimal side? What is the minimal processing and memory support we can provide with minimal changes to the system and program? So since we don't have a lot of time, I'm not going to cover all of these works over here. Some of these are relatively old, so I'm going to let you think about them. But I'm going to go through them relatively quickly. So the first one is, can we change the entire system significantly to get significant benefits? And the answer is yes. And this is actually work that we've done with Sungju and folks at SNU, Junwan. Essentially, we looked at graph processing starting from 2013. And clearly, graph processing is a very, very interesting application for main memory, in-memory computing, because scalable large-scale graph processing is challenging in compute-centric paradigms, because if you throw cores at the problem, you get little speed up, but you get a lot of energy. And the fundamental problem is you get significant random memory accesses in core graph processing algorithms. Not everything is random in graph processing, clearly, but a good chunk of the memory accesses are random, and you have little amount of computation to cover them. So when we did this work a while back, we basically looked at hybrid memory cube, 3D stacked memory plus logic, and we basically combined these hybrid memory cube engines together to an accelerator that we could connect to a host machine. And essentially, these hybrid memory cube engines internally have vaults inside the logic layer, and each vault normally has a DRAM controller. We basically had a very simple in-order processing core over here. You can add a specialized core also, but we added a more general purpose core over here because graph processing has a lot of things that you need to do in a general purpose manner as well. But you could also imagine specializing it, clearly. So what this in-order core does is it controls the memory on top of it, and it basically can communicate with other cores to do updates on other graph processing nodes, other graph nodes that are stored in other nodes inside different vaults in the same hybrid memory cube or across different cubes over here. So basically the programmer lays out their graph, hopefully nicely, so that they can minimize the data movement across the cubes over here. And then they communicate via remote function calls. So whenever you want to update a graph node, you send a message to the core that houses that node, and the update happens that way. So you move only the intermediate data, you don't move the graph nodes from one place to another. And hopefully, you minimize the data movements inside the system. And that's the idea over here. So you can think of this like a primitive GPU that's programmed using remote function calls internally. And we also have prefetching mechanisms that I'm not going to talk about, but they're very important also. Okay, so we get rid of virtual memory in this case. We get rid of coherence. So we can change the entire system clearly. But what it enables is a different paradigm, as you can see over here. Compute and memory are together as opposed to the systems that are processor-centric. And you get 8 terabytes per second bandwidth availability to overall 512 in-order cores over here. And the benefits are significant. Averaged across 5 graph processing algorithms, you get about 13x performance improvement. And later works, there are a lot of works that built on this work actually. They showed that you could get much higher performance improvements if you could get rid of some of the overheads that we have in the system, like scheduling overheads, do better data partitioning in the system, etc. And those are very, very interesting. And I think they showed performance improvements closer to 2 orders of magnitude building on this Tesseract work. And I'm not going to talk about this more, but you get commensurate energy reductions as well. So this is one example of 3D stacked memory giving you a lot of benefits on a particular application. Clearly, this comes at a cost, which is changing the entire system. Then later, we looked at less intrusive approaches. Can we do some simple function offloading? And we have some works in this area, but I'm going to focus on this particular work that we did with Google. Essentially, we wanted to examine processing near memory inside these consumer devices, where energy and area are clearly first-class concerns. And we wanted to look at 4 different workloads that are important to many people in the world. Whether knowingly or unknowingly, we're all using these workloads. And we quantified the energy cost of data movement. As I mentioned, we found out more than 62% of the total system energy is spent on data movement on these workloads. And we wanted to examine the solution of moving computation-close data in 3D stacked memories. And the key challenge here in a mobile computing system is you have even more limited area and energy budget. So our second observation actually helps us. We find that a significant fraction of the data movement often comes from simple functions. I'm going to give you some examples of this. Essentially, if you have simple functions like row copy, for example, you can execute them on a small embedded low power core inside the memory, or small think function accelerators, or reconfigurable logic. I think there's a lot more work to be done in this area also, actually, to understand what should be the substrate. I actually think that the substrate should be heterogeneous near memory. So overall, offloading these functions reduces energy and execution time by about 2x. If you read the paper, you will see that it's about 2x. It's not 13x like we discussed earlier, but 2x is still quite good, I believe, in terms of the simplicity of the system. So let me give you an example of these functions very, very quickly. I'll pick the example of TensorFlow in this case. Essentially, we looked at DNN inference using TensorFlow and a number of networks, and we found out that more than 50% of the inference energy is spent on data movement, and more than half of it is spent by two functions, packing and unpacking and quantization. And I'm not going to go through these in detail, but packing and unpacking are, you reorganize the elements of the matrix to maximize computation efficiency, essentially. And it's a very simple data reorganization process. Quantization is employed by all neural networks that I know of. You basically, instead of using large, complicated data types, you use small, simple data types to improve inference execution time, energy, and consumption. And quantization is also a simple data conversion operation. And you can actually offload these to simple cores or more sophisticated accelerators specialized for doing this on the memory side, and you get significant benefits, as you can see over here. And you can also see some other functions that we looked at in the Chrome browser. You see compression, decompression, texture tiling, color blending, and in the video playback and capture, we have motion estimation, for example. People already design accelerators for this in the compute-centric paradigm. Basically, we move some of those accelerators to near data. Okay, so you get significant energy and performance benefits. Clearly, specialized accelerators provide you even more performance energy benefits compared to a simple course. Okay, so I believe this is really promising going forward. There are issues to be resolved also that I'm going to talk about, but there are many, many more examples of this. I'm going to give you examples from our work, but clearly there are other works that I will point out in a survey paper that I'm going to mention later. In GPU systems, you can do this. In data structures that are pointer chasing, for example, you can do this. Similarly, you can do this transparently to the programmer also. We also accelerated prefetching mechanisms like random execution near memory, and they're much better if they're accelerated near memory, in my opinion. And more recently, we've looked at FPGA-based systems that incorporate HBM type of memory. This is also near data in a sense, maybe not exactly as near data as we would like, but on real FPGA systems, you also get significant performance benefits compared to DDR4-based FPGA systems. And as I mentioned, on bioinformatics, you can accelerate approximate string matching type of algorithms with algorithm architecture co-design. And I'm not going to talk about these in more detail, but clearly there are many, many more case studies that are done that show the benefits of near data processing. I will very briefly mention what is the minimal processing in memory support we can provide, because I think that's also important. And this is another work that we've done with Sungju and Junhwan et al. Essentially, we wanted to minimize the system cost, minimize the changes to the system, and we want to have no changes to the programming model. And the idea over here is if you want to do something like that, you want to expose the processing in memory operations as cache-coherent virtually addressed processor instructions that operate on a single cache block. And this is one example, PIMAT. So this leads to no changes to the programming model. You're still sequential execution, no changes to virtual memory, no changes to, minimal changes to cache coherence, and no need for data mapping across memory modules because you're already operating on a single memory module if you're limiting yourself to a single cache block updates inside whenever you're doing processing in memory operations. And the second key idea is dynamically decide where to execute these instructions on the processor or on memory. And I think this is really important for any type of processing in memory engine. Even though the programmer potentially suggests that this should be executed near memory, there might be reasons why you cannot do that because the near memory execution engine may be, for example, used by somebody else, right? Okay. So very quickly, this is the programming model. It's not different from the programming models that we have today, sequential execution. What is really interesting is what kind of operations can you offload. And this is really application specific in the end. So I believe going forward, looking at more customizable ISAs that can be implemented on reconfigurable fabric near memory is going to be interesting. So there are some example operations like dot product operations near memory, Euclidean distance. So you can see that these all operate on a maximum of a single cache block. And these are important for time series analysis, for example, or machine learning applications, and there are more you can see over here. So what are the results? Very quickly, we looked at important applications, data intensive, and the performance improvements are not as good as the previous approaches, clearly, because this is minimal. but they're not bad, I will also argue. It's about 47% on large input data sets. And you can see more analysis in the paper for smaller data sets. Large input data sets are where processing in memory really shines because you're not bound by the caches. And the energy reduction is also significant, as you can see in large input data sets. So I believe this is really interesting because this is an approach that enables simple modifications to the system. Of course, you need to be able to modify the ISA. There are approaches that we've also looked at without modifying the ISA, but the benefits are actually even lower than what we get over here, like the paper that I mentioned earlier, transparent offloading and mapping, looks at without ISA modifications, and the benefits we saw over there was about 30% or so. Okay, this brings me to eliminating the adoption barriers. So clearly, whenever you have a paradigm change, especially if the paradigm change is really coming from hardware and hardware changes, you're at a position to actually essentially change the entire software of the world. And that's not an easy task, clearly, because you need to think about adoption going into the future. And there are a lot of adoption issues in processing in memory. There were a lot of adoption issues in GPUs also, but processing in memory takes it to another level, clearly, because GPUs are still processor-centric, compute-centric. Processing in memory is a completely different paradigm. So I will very quickly go over these. I'm not going to go into the details, clearly. And these are all, I believe, research opportunities. And I believe these are good research opportunities because they solve some of the important problems. So we want to look at functionalities of PIM and application and software for PIM. And I think I gave you some examples of this. There need to be more studies to understand what kind of functionality is really important in PIM. How do we write application and software for PIM? And there are different types of PIM, as we discussed. And maybe different types of applications benefit from different types of PIM. So that doesn't make things easier, clearly. But maybe there's a unified framework also for these different things. Ease of programming is a clear issue. How do we design interfaces to make it easier? How do we design compiler and hardware support to make life easier? Can we do it completely transparently? I believe there's a limited use case in that case, but can we do it a little bit more transparently to the programmer with some compiler support? How do we provide system support that's important for general purpose systems of today, coherence and virtual memory? I believe these are not easy. Virtual memory is very difficult. People are rethinking virtual memory today for various reasons. I believe there needs to be more rethink to be done on the processing memory perspective. How to design the runtime and compilation systems to make things easier for the user and the programmer, adaptive scheduling, data mapping and access and sharing control, security, etc. And finally, how to design infrastructures to assess benefits and feasibility in an intelligent manner that the users and programmers can use. I believe these are not easy. They're tough. But I believe all can be solved with a change of mindset. And in my opinion, in many cases, the mindset is the limiting thing. Usually when you present some of these ideas, for example, to people who have the horse-like mindset, let's say, they have the blinders on, they cannot see anything beyond that blind spots that they're used to seeing over here in front of them, then then the answer is, oh, this will never happen. Clearly, if that's the answer, no change can happen in the world, right? If the immediate reaction to a change is this will never happen, then you're guaranteed that that change will not happen. So it's good to have a better mindset to ensure that this can potentially happen. In the end, maybe it will never happen, potentially, but we don't know that yet. As a scientist, we have to discover all the options to make sure that a better world can potentially happen, right? Okay, so I believe we need to revisit the entire stack in the end, and I believe we can get there step by step. So we need to start looking at both simple approaches and more complicated approaches too. So if you're interested, we actually recently wrote this large book chapter that talks about different aspects of processing in memory, as well as different research directions going into the future. This was written in December, and you can find it online, as you can see over here. And I'm happy to talk about it in more detail. I believe it's a very fruitful area of research, and the findings that we find could be useful for many, many systems. Okay, there are also other reviews. This is a little bit older, but it has a different flavor, if you can take a look. So there's more hope than actually you may imagine. Clearly, there's work that showed that these in-memory bulk bitwise operations are possible inside systems, but there are also companies that have actually manufactured chips that do processing in memory. This is an example company, UPMEM. What they've done is they've taken DRAM modules and they basically put a simple processor inside each bank. So you can think of this as near memory processing inside the DRAM itself. So they don't modify, they don't use analog computation capability, but they really put a very simple processor near each bank. That processor is limited to the data that it has in this bank. Unfortunately, it's not connected nicely to other processors inside the chip, but this is a good start, I think. And we've been working with these folks at UpMem, analyzing their systems and looking at where the system is good at or bad at. And we have a paper coming up that describes our learnings in Sigmetrics 2021. And if you're interested, I'd be happy to share an early version of it. Okay, so I think this is very interesting clearly because folks have already designed this and we have real hardware that is working, doing something inside the memory chip. Okay, so let me go over these key challenges very, very quickly. I'm not going to talk about these in detail, but you can see some papers that are example studies. I think coherence is a tough issue. Virtual memory is an even tougher issue in main memory. And we also need to look at data structures for PIM as well. Okay, so basically, I think a big challenge and opportunity for future is designing computing architectures with minimal data movement, how to design more data-centric architectures. Okay, so I think at this point, I will probably ask the question to Jay or others. I can cover the related data-driven and data-aware directions in 10 minutes, or we can skip that and get questions. I will conclude and we take questions. Yeah. Okay. Yeah. Okay. Okay, sure. Sure. Mhm. Let me check the chat if there are any questions that arrived. Okay, I don't see anything on the chat, but I'm happy to take anything with Mike also. Mm-hmm. 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 Yeah, that's a very good question actually. So I think FPGAs are a good place for sure, and that's what we've been doing with our studies. I think FPGAs, there are some memory controllers clearly that are open, but there are some that are not completely open. So I would suggest looking at FPGAs. There's also some other work that are more open that you can use. There's this DRAM Lite work. I don't know if you're aware of it. But if people search for it, they can find it. It's called DRAM Lite, and it's a project. Essentially, looks at different memory controllers for different DRAM standards, and I believe it's completely open. That one. So that's what I would suggest. I think finding an open enough memory controller to build on, and working on an FPGA, of course, is important in my opinion. In the end, because you can do a lot more, I think, on an FPGA. Because the time scales are better in terms of simulation, especially if you want to evaluate workloads going through the memory controller or do some memory testing. So I agree that unfortunately there's not enough openness compared to the openness we're experiencing in the core levels. But I think that's going to change also going into the future. Yeah, sorry. Sure.
compute nodes, like CPU have very different manufacturing procedures. And even if we find a way to combine those two components into one, would the real commercial companies agree to do it, like Samsung and Intel cooperating together?
Mm-hmm.
I think this is kind of intellectual property problem since many details of memory controllers the CPU companies have are black box and they don't want to share it. I want to hear your opinion about whether these team researches will show in real products in 1 or 2 decades, or
Mm-hmm.
will it fade out and remain in armchair research in like 50 years when the computing paradigm is substituted by some new era like quantum computing?
Yeah.
This was like my original question, but you lastly mentioned about UpMem
Mm-hmm.
as the result.
Mm-hmm.
In this case, will it become like more generally useful, like to customers
Mm-hmm.
or to researchers?
Yeah, yeah. So that's a very good question. Clearly, I don't know the answer to the long term question, but we can only do the research and try to do our best. I think as researchers, work with the companies, showcase results that show where these ideas can actually be really beneficial. But I will give you two answers related to. One is related to UpMem. I think UpMem is a very promising example because they were able to do it and they did it and they have real systems. They're scaling it up. It remains to be seen, of course. I mean, their architecture has a lot of limitations also. I think the lack of communication, for example, between different processing units inside the DRAM is a problem in terms of enabling more applications, meaning being more general purpose, as you mentioned. And general purpose at some point is very, very interesting. So I think we need to overcome some of those. Some of those are going to be not so easy to overcome with the technology that we have. Like the DRAM process is not very good at adding a lot of interconnects inside the DRAM chip itself. With 3D stacking, I think we can overcome some of those. So I believe 3D stacking can alleviate some of these concerns, even though it may not get as much benefit as inside the DRAM computing. So I think this means that we need to start exploring and start, I don't know, building companies, working with companies who are able to do this, to actually understand the benefits and the downsides of different design choices. And that's how we can actually enable, maybe see the answer 50 years down the road, or 20 years down the road, or 10 years down the road, right? I don't know what that will be. And I think the answer will be promising. I think today people are actually seeing the downside of the huge data bottleneck. And as a result, these efforts are being spent. A lot of money is spent on exploring these new paradigms, for example. The second answer, I think, okay, aside from the UpMem, so startups, I think, are a good opportunity, for example, to get these into the products like UpMem. But also, I think looking at these simple approaches to change the system in a simple manner can be very beneficial. Like I mentioned, row clone. Maybe Ambit is the next step after row clone, but similar operations that are simple enough to not cost a lot into the system, and that are demonstrated to have some proof of concept, even in existing real chips, existing chips without modification to DRAM. I think those are very promising, and I think those are actually easier to implement from a company perspective. But here, I think the company needs to be a little bit more open to the ideas. So I think some of the this gets our discussion into the mindset, because if you think about cost, row clone is not. It doesn't add a lot of cost into the system, so it's implementing is not very hard. There are multiple issues. End-to-end system issues is important. What kind of benefits do you get end-to-end? And actually, we have a lot of results end-to-end today, showing that you still get a lot of system performance and energy reduction end-to-end. And we're actually building enabling systems end-to-end for row clone and in-memory operations also. So that's all good, and I think as researchers we need to do that. We need to work with companies to do that. But there's also some inertia in the companies that's very unfortunate, I think, that needs to change also. If you look at these heavily invested companies inside DRAM, unfortunately, even simple things like row clone, sometimes they're averse to taking risks, and some of it is understandable. Some of it is not so understandable. Some of it is real, I think, a risk because if they implement this function, okay, maybe they will lose something in terms of area, and this is a very area-driven market. But I think a lot of the risk is exacerbated compared to the potential benefit. Sometimes you need to take risks to actually take your business to the next level, right? And I think if you take risks, like maybe some simple risks that are not very costly in the end, you're still risk averse, but you can potentially see what the market is, because in the end, the answer to the question of, for example, who will really benefit from this is not easy to answer without doing a real product and putting it into the market. So you can do all these studies that we have done, that others have done, that others have been doing in simulation or some prototypes, but they will always be limited in the sense that the real benefit you can never measure, because you cannot see the real benefit in applications that are outside. But if you have a product that has row clone, let's say Ambit, I'm just picking those because I just described them, right? Then you can say, okay, my cost is this, I'm going to charge you this much. Buy it if you're going to use it, and if no one buys it, yes, you will lose a little bit cost, but maybe that cost is bearable, right? So I think there's this risk versus benefit equation that's unfortunately heavily biased against the benefit, in my opinion. Of course, maybe the companies have a better answer to this, but I have not heard a better answer from the company. Yeah. Sure. I hope it's useful. Okay, now I see some things. Let's see. So I have a question from Brian saying, what do you think about the role of coherent interconnect technologies such as CCIX, OpenCAPI, and CXL in terms of removing the adoption barriers of processing in memory to the real field? That's an excellent question, and I think those technologies are actually very good. I think of these as synergistic technologies that can enable in-memory computation in a more seamless way because they're coherent already. I think their coherence may not be, maybe we need to improve the coherence that they provide going into the future, maybe make it even more finer grained, for example. But I think definitely those are good. So we have done some studies, for example, with OpenCAPI or CAPI with IBM Power 9, the NEO work that we published in FPL that looks at accelerating weather prediction using high bandwidth memory technologies are essentially using OpenCAPI. And we see a lot more easier programmability with those technologies. So I think we need to work on combining those technologies more with processing in memory, no question about that. Okay, Giho asked, excellent talk, Onur. Nice to see you, Giho. And I'd like to ask your view about the influence of the DSA, domain-specific architecture, on the PIM or NMP approach. As you said, would it be more suitable to use new data-centric, data-driven, and data-aware architecture for DSA? So I think, yes, certainly. I mean, domain-specific architectures are by nature, you can express more about your data because you know the domain much better. And I think certainly data-aware architectures are easier with domain-specific architectures. If you can specialize within a domain and specialize your operators as well as operations and data types to a domain, and specialize also your interfaces to a domain, by nature, you're more data aware because you can communicate more. By nature, you can also be more data centric because you can express more about your computations to the memory system. Data driven is a little bit different, I think. So I think we have not talked about data driven clearly much in this talk, but I think data driven can also benefit from domain specific because now you can actually input more information about the domain into the learning algorithms that you can employ inside your controllers, for example. So I think domain knowledge helps all of these, no question about that. Domain knowledge will help PIM in terms of your data alignment, for example, and data mapping as well. So everything gets easier with domain knowledge. Coherence becomes easier. Potentially virtual memory becomes easier also because you may not need a lot of virtual memory if you know about your domain and if you know how your data is laid out, right? So that's a very good question. I think these are synergistic again with processing in memory, and I think it'd be good to see more work in this domain, in domain-specific architectures for processing in memory. Okay, one more question from Brian. The second question is, what do you think about the importance of computational storage drive, not memory, compared to the computational memory? Okay, that's an interesting question. I mean, I think I don't want to necessarily compare these things. Okay, if I have to, I can compare clearly. In my opinion, both need to be done. Basically, there are benefits to doing computational memory, processing in memory. Clearly, there are many applications that fit memory that need the latency requirements of low latency of main memory that may not do very well on a storage device, on an SSD, for example. There's a reason why we bring things into the main memory, because the latency is very low, and the energy characteristics may be better as well. So I think this space needs to be explored more. But in my opinion, we need both. We need computational storage as well as computational memory. There may be use cases for computational storage for very, very large data applications. But I think computational storage itself is a hybrid system as well. So in computational storage, you don't want to do computation just inside the SSD, but also potentially think about doing the computation inside the memory as well, because you have a good chunk of memory as well in the computational storage device. But again, I don't want to necessarily compare. The big benefit of memory is latency, clearly, and energy. The big benefit of storage device today is the huge capacity that you have, and potentially more easier combination with the memory technology that already exists there. But in the end, I believe we need both. Okay, one more question. What do you think about GPU like Bluefield introduced by NVIDIA? Do we need an accelerator for data processing? In terms of memory-centric computation, I think it's promising as much as research about NPU right now. I just want to hear your opinion. So that's a good question also. I don't know enough about GPU, I think. I've read and heard presentations about it. And I think it's a good idea. I mean, in the end, it's good to accelerate data processing for sure. I think Oracle had some similar idea at some point, although they canceled the project. What was it called? I think it was called Rapid. I believe NVIDIA's idea is toward that direction, maybe more customized for a GPU system. But I like the idea in the end. If you can accelerate data processing, you will get some of the benefits of what we've discussed, but not all of the benefits clearly. It also depends on where you put the DPU. If you put the DPU inside a 3D stacked memory in the logic layer, clearly it becomes more similar to what we've been discussing. But I think it's a step in a good direction for data handling. But maybe it's not as aggressive as in the end it should be to minimize the data movement. Okay, Sungjun says, I think that the data movements between memory chips is also important due to the large memory footprint of applications, e.g. deep learning. This might also affect the utilization of PIM because it suffers from the available bandwidth between chips. I want to hear your opinion on this issue. Thank you. So yes, for sure. In the end, whenever you're doing processing in memory, you want to minimize the data movements that you have across the memory chips. So this was an issue with Tesseract, for example. Tesseract was limited in terms of its performance because in the end, at some point, because you cannot perfectly partition your data such that the chips, the data only stays within a memory chip. You have to go off chip, and those off chip memory accesses or off chip communications, in the end, the bottleneck in your system. So absolutely, in the end, I think we need to minimize that data movement somehow. But I mean, there, I think you can say that we're back to square one. But I think we're better than square one because we still can do some processing. As long as we can localize some amount of computation, we're eliminating the data movement. And then you're left with data movement across the memory chips. Now, you want to minimize that data movement with algorithmic techniques, architectural techniques. And also, I think, with techniques that enhance your memory chip, right? Maybe with better memory chips, better die stacking technologies, better monolithic integration, you minimize that data movement across the memory chips as well. But fundamentally, clearly, your data is going to be much larger than a single chip will handle in the end. And you'll have to bear the cost of a cross-chip data movement somehow. But it's going to be better than what we have today if you have processing capabilities inside the chip or near the chip with 3D stacking technologies. Okay. Okay, Jae-Yun says, in the case of implementation of PIM with the minimized change, is there any power problem in DRAM even though PIM reduces energy consumption a lot? I think adding logic in DRAM and maybe activating more data from DRAM cells simultaneously can require more power, and I wonder if it can threaten some power restrictions of DRAM specifications. So that's a good question, and yes, in the end, nothing comes for free. If you're doing computation inside the chip, you have to pay more power. But I think, again, it doesn't the benefits that you get, I believe, outweighs the power cost. And we also need to take a different approach to DRAM power going into the future. So DRAM is currently designed as a memory device, right? And all of the power specifications is there because it's a memory device. If you actually use it also for compute, I think we need to change some of the power specifications. For example, the peak power has to go up, no question about that. But that's true for a compute, any other compute device as well, right? Any other compute device, a GPU, a CPU. We don't have the same power restrictions that we have in DRAM because they're compute devices. So I think we need to change the mindset in terms of thinking about power consumption and also thermals of DRAM devices. We may need heat sinks for DRAM devices, of course, depending on where you employ them. But I think like the TFAW, for example, for activate windows, those kind of characteristics, I think we need to rethink some of those going into the future, because they will be limiting your performance if they're solely there to limit power. And I think that's a very good direction also. How do you actually design a DRAM chip to have good power and good reliability characteristics that can sustain in DRAM computation? That's, I think, a great research topic as well. Sure.
So, in many PIM studies, people assume like HMC style DRAM,
Mm-hmm.
they actually have asymmetric bandwidth between off-chip versus internal
Mm-hmm.
bandwidths. But HMC is actually pretty much dead, and HBM is the mainstream stack nowadays. So in that case, we don't have much difference between bandwidth to the host versus internal bandwidth.
Mm-hmm.
So that the question is whether is still this near data processing or in-memory processing still valuable in such even in such setup, or we need like newer DRAM devices, or we resurrect to make more viable.
Sure. Yeah, that's a great question actually. So I think I probably would say everything. Yes, yes to everything you said. I think let me answer the first one. Is it still beneficial? I think the answer is yes, from an energy perspective especially, and maybe from a latency perspective less so. So bandwidth, yes. So bandwidth is part of the benefit of processing near memory in the 3D stacked manner as we discussed. But there's also latency benefits and energy benefits, and I don't think you can get the latency benefits and energy benefits even if your bandwidth is constant internally versus externally, if you don't do processing inside the logic layer. So there are some applications that would benefit from latency and energy clearly. And even if the application doesn't benefit from latency, it could benefit from the energy, even though it doesn't benefit from bandwidth, for example. But the second thing is, I think HBM is interesting, but we should be perhaps looking at more suitable memory chips or memory designs within the context of 3D stacked or monolithic 3D memories to provide better processing in memory or near data processing capabilities. So that's why I said yes to everything you said. I don't think these are exclusive. Okay, one more question I saw. Okay. So I will answer this, and if you let me to conclude and acknowledge my students, I will do that also. Because this is their work in the end, right? Okay, would you have any work that you have done on processing in storage or computational storage that you can share maybe at the next seminar? So that's a good question. Thank you for asking it. So we are doing some work at this point. Unfortunately, we don't have anything that we published. It's all in progress. When it's complete, I'm certainly happy to share it in a seminar. Maybe it won't be the next seminar exactly, depending on when you envision the next seminar to be. But I'm happy to share it. And there are some interesting directions here, for sure. And clearly, there are other people who have done work in this area that showed interesting results. Certainly, I've seen that work from Samsung that have looked at processing in storage. There was work from MIT, the Blue DBM work, for example. I think Samsung had the Biscuit work and other works more recently. As well. Okay, so should I finish very quickly, unless you want me to do something else? Okay, so I didn't conclude, but I think basically I will emphasize that we need to revisit the entire stack. And I think we need to exploit good principles, but I think most importantly, more than anything else, we need open minds, because open minds, I think, get us to new principles, or good principles. And I didn't mention all of these principles, but they were implicit in the talk. And I already mentioned these works. So a longer version of this talk actually exists. I gave a tutorial at IEDM, and we posted the video online. If you're interested, you can look at it instead of waiting for the next seminar. So I will acknowledge people who have funded our work. It wouldn't have happened without that funding, clearly. And I will acknowledge my students, my research group, who clearly have contributed to all of this work that I've described, and they've done the work. And if you're interested, we have released a newsletter much recently in the style of, I guess, the pandemic. You can see over here. There are more works that we have described over here that have happened over the course of 2020. Feel free to take a look at the newsletter. And thanks for listening, and thanks for the many good questions that were asked during the course.
Thank you very much, Onur. Actually, the newsletter is really cool. I'm receiving it through your LinkedIn account, but that's actually quite good.
Okay, thank you.
I really appreciate your talk, and then I feel a lot of energy from you and the audience. It was very nice event. It was a nice talk. So we hope to, as I said before, I really want to hear the second and third pillars of your work.
Mm-hmm.
So we hope to invite you in soon.
Yeah, I'm happy to give a version 2, focusing only on those portions as opposed to going through the first half. Thank you, Jay, for hosting me.